Hello everyone, my name is Liia Butler, and today I will be presenting the work that I did alongside with Professor Geoffrey Challen and Professor Liia, entitled Data-Driven Investigation into Variants of Code Writing Questions. To get started, imagine an instructor of a large computer science course involving coding. They offer online exams to assess students. Paper exams require tedious manual grading, and grading can be inconsistent. Meanwhile, online exams offer the ability to incorporate a code editor, compiler, and automated test cases to alleviate grading burden and provide consistent grading. They also offer asynchronous exams, where students are not taking the exam at the same time. This offers flexibility to students. However, this also makes them vulnerable to collaborative cheating, when one student who has taken the exam supplies information about the exam to another student who has yet to take it. To defend against collaborative cheating, they use the strategy of question variants, which we define as manually written questions being put into a pool with other variants and aim to assess the same learning goal. In this instance, as they're writing a particular exam, they want to ask a question about linked lists to their students. Specifically, they ask to write a method in Java to accomplish a given task that requires iterating through a linked list. The linked list class is set up the same, with a linked list of items with a value and a pointer to the next item. The linked list class has a pointer to the start of the linked list. The instructor poses it as 4 different variants. Variant 1 is count number of even value items with an example solution found here. Variant 2 is count number of odd value items with the example solution found here. Variant 3 is count number of positive value items with the example solution found here. And variant 4 is count number of negative value items with the example solution found here. If we put all 4 of the example solutions together, we can see that potentially only the comparison on line 8 needs to change. So we can now put all the question variants into the pool. Variants are assigned at random, and each student gets 1 variant and 1 variant only. And from their perspective, this was their question on linked lists. But now we have 2 competing goals in these variant designs for online asynchronous exams. Do these deter collaborative cheating, and are these variants fairly assessing students' knowledge or skill? Prior research has investigated the first goal. We will be focusing on the latter one of how well question variants can accomplish fair assessment in the context of online asynchronous exam settings. Given this, we propose a data-driven investigation into these variants. We apply our investigation into a dataset of 3 midterm exams from a large introductory programming, further known as CS1 course. Our results show that observable inequalities of student performance exist between variants, and these differences aren't just limited to score. We also show that the information gathered from our investigation can be used to provide recommendations for improving design of future variants. To give a little bit of data context, we examine coding submissions from 3 midterms of the fall 2018 semester of a large CS1 course taught in Java. These were 50-minute long exams, and details about the exam and the question breakdowns can be found in the paper. But we will be focusing on what will be known as E3Q1 linked lists, which corresponds to our linked list example as mentioned earlier. These exams were held in a computerized assessment center on an online homework and testing platform, and again, more details can be found in the paper. Students were also evaluated on code quality using check style in addition to functional correctness. Each raw submission is processed into a submission data type representation. A submission has the question ID, user ID, score received, submission code, timestamp, result, which I'll touch on in a second, and feedback, which would be the output when submitting the code. The result is the category of end result of a submission, and a submission is classified into one of 5 result categories: check style error, compiler error, runtime exception, failed test case, and correct solution. Now we move into our actual investigation of student performance using our investigated dimensions. Our three dimensions are score, solving duration, and distribution of effort, and we use these three dimensions to answer the following research questions. What inequalities of observed student performance exist among question variants? And how can an investigation results be used to derive recommendations for writing future question variants? For score, we consider the overall distribution of the highest scores of those who attempted a variant at least once and test for statistical significance. For solving duration, we calculate the attempt duration, which details of that process can be found in the paper, and then test for statistical significance. For distribution of effort, we identify 5 types of student efforts. First submission, resolving check cell error, resolving compiler error, resolving runtime exception, and resolving failed test case. We sum up the time students spent in each resolving category for the given question variant. The metric provides further insight on a particular sticking point on a particular variant and also provides quick insight on student behaviors towards a particular question variant as a whole. Looking at the score results, most questions do not show statistically significant differences among variants, with the exception of our linked list question, E3Q1. With our E3Q1 score, after pairwise comparisons, we find statistically significant differences between variant 1, count even, and variant 2, count odd, as well as variant 2, count odd, and variant 3, count positive. Moving to solving duration, we can see that there are statistically significant differences for 4 of the questions asked, including our E3Q1 linked list question. We provide insights into the other 3 questions, but for now we stick with our E3Q1 linked list question. So for E3Q1, after pairwise comparisons, we find statistically significant differences between variant 1, count even, and variant 2, count odd, variant 2, count odd, and variant 3, count positive, and variant 2, count odd, and variant 4, count negative. So E3Q1 variant 2 both performs more poorly compared to other variants for the same question, and we can also see that students are spending more time solving the question compared to all variants, which now potentially eats into time needed to answer other exam questions. This can compound if a student receives multiple variants in an exam that are significantly more time consuming than other variants in their respective question pool. Moving to our third dimension, while we use it for informational purposes, we can use the distribution of effort to narrow focus. In particular, here we see considerably more effort spent resolving a failed test case in variant 2, count odd. Using these results, we can now see the inequalities of observed student performance that exists among question variants. Moving to answer our second research question, we now derive recommendations for future variants. So for E3Q1V2, or count odd of our linked list questions, we had our suspicion about a misconception of the percent operator. In Java, this is the remainder operator, which is different than the mathematical modulus. We suspect students fall into the common pitfall of using n mod 2 is equal to 1 to check for an odd value. This would cause a failed test case when there is a negative value present, and we can see how the expression would change in the example code. Manual inspection of submissions resulting in a failed test case result shows that this misconception is indeed present. We could then make the recommendation that these questions use the operator consistently across variants, for example, testing for multiples of a given number. Only requiring information extractable from submission records allows our investigation to be generally applicable, but external and human factors are not captured. We also exclude variants that do not have a submission, so we do not know why a variant has influence on why a student does not submit. For example, a student could have looked at the prompt and deliberately skipped it, ran out of time and didn't even see the question, or even attempted to solve the question and simply forgot to submit. Our duration approximation is limited. It assumes that a student immediately begins focusing on the next question variant. This decision leads our analysis to overestimate solving duration, particularly for when a student first begins a question variant, as more time is likely to pass, and a student could be focusing on more than one issue as indicated in a submissions result used in the distribution of effort dimension. So in conclusion, we present a data-driven investigation for analyzing variants of code writing questions in online asynchronous exam settings using 3 dimensions: score, solving duration, and distribution of effort. Observable differences among variants exist, and this is not just limited to score. And results can be used to provide recommendations for improving future variants. Overall, this work serves as a step towards constructing best practices for designing these variants. Thank you.